Hi, my name's Alex, and I'm going to show you the EPS ground support software. So this is a support software that you can use by plugging a micro USB cable into the EPS and running the software. And basically what it does is it streams telemetry directly off of the EPS and plots it into some nice graphs, as well as it does some nice math on it. And it's a little bit easier because you can see the data in real time as it's coming off the EPS. So it's great to use this software while you're running tests, and you can just visually confirm things are looking okay. It's a great tool for just monitoring what the EPS is actually doing while you're running tests and just making sure that everything looks okay. Before we get started, you have to turn the EPS telemetry collection system on. So by default, the EPS does not actually start collecting telemetry. All of the sensors and the microcontroller that collects the telemetry and does the math on it, it's all turned off by default to save power. By default, the EPS telemetry collection system, or the power monitoring unit as its official name, power monitoring unit, it monitors power and it collects telemetry. So I might use the two kind of interchangeably, telemetry collection system or power monitoring unit, PMU, just know that they're the same thing. By default, the power monitoring unit is off on the EPS, and that's to save power. While that telemetry is very good and it's crucial for day-to-day mission operations, the default mode is just to turn it off. It does not turn on by default when the EPS turns on. It requires a command from the OBC to actually turn on, or there is a jumper on the nadir face of the EPS called on TLM, and that jumper will also force the telemetry collection system to turn on. It's perfectly fine to insert the on TLM jumper and at the same time have the onboard computer turn on the telemetry collection system. Nothing bad will happen. It's just not a great idea to do that because if you're running tests or you're trying to reset the telemetry collection system from the onboard computer, you can't do it with the jumper inserted. The jumper just kind of overrides the onboard computer and it forces it to stay on indefinitely until the jumper is removed. The jumper is really just designed for use when the EPS is not integrated into a satellite and it's just sitting on a bench and just running tests with just the EPS itself, versus if it's in the satellite, like I'm going to show you, it's best to use the onboard computer and the Houston software to actually turn the power monitoring unit on. So let's do that. I'm on the ORCAsat computer here. So this is the computer that's plugged into ORCAsat. Just so I can show you that what ORCAsat looks like. This is ORCAsat. So this is a webcam that's plugged into the computer and it's just streaming a live view of ORCAsat. Anyway, we're gonna launch Houston here. And this is not a tutorial on how to use Houston or anything, so I'm not gonna spend too much time, but all I'm doing is I'm just loading up the Python virtual environment, and now I'm just launching Houston in Python, and I'm just in the GCS folder where all these files live. This is not a tutorial on how to install Houston or anything, so we'll just wait for this to load up. So Houston has loaded. First thing I'm going to do is just ping the spacecraft, make sure I'm actually plugged in and talking to it. Okay, so the firmware is loaded and I'm in safe mode, so that's fine. I am just going to send the command set EPS power state, and the argument is on. So the command is set EPS power state, all underscores, all lowercase, and the argument is on in capital letters. And there we go. So we got confirmation that the EPS is now turned on. And if we really want to confirm that, we can use the command get EPS power state. And that'll also confirm that it's on. And that's all we have to do. We don't have to do anything else in Houston. The EPS ground support software will take over from here. So on ORCAsat computer, the EPS ground support software is just on the desktop. It's just an executable that you can run. It's pretty easy. So we're going to launch this. And we're going to connect to it. And it's usually just the last COM port. Because you just turned the EPS on, the COM port will show up. And it's usually like the bottommost COM port. And in this case, it should show up as connected head flight candidate 2. Then you want to hit this little play button here to actually start streaming data off of the EPS. So in the default view, you've got voltage monitor, current monitor, and temperature monitor, and this will just plot the data. And there's quite a few channels as you can see from the gear wheel here. So you probably don't want to have all of these channels running in real time, especially on ProtoSat, because there's no ADCS in here. So for things like all of the IMON ADCS channels, you can just disable those and it won't plot them. As well as we won't be using the GPS, we can turn that off, and we won't be burning the antenna, so we can turn the IMON burn off. And up here we can get rid of the test point. Yeah, so in this view you can see kind of what's going on. If I go back into Houston, so go back into Houston, it's kind of cool because we can actually do things like set payload power state to on. We should pay attention to the fact that there is no 12-volt signal right now. And if I hit on, we should now see that the 12-volt will turn on. There we go. So now we've got 12 volts, and that's on VMON 12 volts. So we just turned the 12-volt regulator on to turn the payload on. And as you can see too here, it looks like the BCR current has also increased, and it looks like well, actually just all the currents. IMON pack has also increased a little bit. And what is that? 12 volt has increased a little bit, as you would expect, while 3v3 CDH just kind of has stayed static the whole time because the onboard computer is on and running. And as you can see, temperature too, you can see, okay, so the PMM is warming up a little bit. This is probably since we started streaming data off of it, as well as just when we turned on the 12 volt regulator, you can see this guy right here, which is, spoiler alert, TMON 12 volts. So the 12 volt regulator is increased by about a degree Celsius above the rest of the board just from turning it on. This is really easy to see what's happening. If you've got loads that are switching on and off relatively fast or slow, this is a great tool just to plot and see what the current's doing in real time. You won't get this kind of data off the satellite, obviously, when it's in orbit. We've only got one ground station, so we can't stream data off of it like this, but it's really very useful for doing mission-like tests and then streaming data off of it while you're doing mission-like tests and seeing kind of like how the onboard computer is operating and how the transmitter is operating and turning on and transmitting and that kind of thing. So this is a very useful view, and the graphs are quite handy. And you can zoom in and, you know, select a certain area and whatnot and plot it. So it's a pretty nice tool. The other tabs aren't as useful, but they're great just to see numbers. So this is the voltage stats tab. You get a min, max, and a mean on the voltage. This is just a good way to basically look at the means and just make sure everything looks okay. So for 12 volt, you can see the mean is low because when 12 volt is off, it's a boost regulator. Basically, it's just going to be one diode drop below the battery pack voltage. Registers as 5 volts. Once you turn on, it goes to 12 volts. If we reset these, the min should just populate now with 12.45. And if you're looking at these voltages and you're wondering why these are a little bit high, like for example 12 volts 12.4.5, 5 volts is 5.18, and 3 volts is 3.35, it's because all of these voltage converters have power save mode, where basically they switch between pulse width modulation and pulse frequency modulation. Pulse frequency modulation, they don't regulate at a certain frequency. They change the frequency that they're switching at, and they slow the frequency way down because you don't need to switch as fast when you're drawing light loads. The downside to that though is that if you're switching that slow and you've got a huge transient, like something switches on and draws a ton of current, the voltage will droop quite a bit before the regulator can switch back into pulse width modulation. And so that's why the voltage is regulated a little bit higher when they're in power safe mode, is to give it a little bit of headroom for if something switches on and starts to draw a ton of current. Array voltage is just going to be the maximum PowerPoint tracking voltage. In this case, we're plugged into a power supply, not a solar array, so it's not PowerPoint tracking, and this voltage is just whatever the output of the power supply is, minus a diode drop or so. VMON BCR is just the output of the BCR, which is basically the same as the pack voltage. There isn't really a big difference there. And the reason why I want those two data points is because there is a low side inhibit as well as a battery protection circuit kind of in between those two voltage measurement points. So if either one of those aren't quite operating right, or they're adding more resistance, or there's a ton of current being drawn and they're trying to dissipate a little bit of heat, you will see a voltage drop between the two. Ideally, VMON BCR should always be higher than VMON pack because we get a very slight voltage drop over the low side inhibit and the battery protection circuitry. And if the battery is discharging quite a bit, you'll see a voltage drop the other way around, where the VMON pack is higher than VMON BCR. It's really just a great way to double check things. For current stats, It's more or less the same as voltage stats. You've got all the channels, you've got min, max, mean, and standard deviation. The main thing of interest here is the charge tab. It actually keeps track of how much current things are consuming over time. So it actually computes the charge in real time. This is a great way to basically have a look at and just see kind of what's going on, because the mean and the min and the max might not paint the whole picture of how much energy something is actually consuming, while the charge is actually computed at a much faster rate, on the order of like a kHz or so, and then it's just updated very slow on the software. But this number is actually computed quite fast, so it can actually detect spikes and peaks, and it can actually pretty accurately compute the charge. And this is great for like punching into a power budget or something like that, and just see kind of like what's the runtime of the battery. And then lastly, you got temperature stats. So temperature stats gives you just a good idea of what temperature things are. And that's basically it. The last tab here is MISC, which gives you one stat that's very, very, very useful. And this is like the most important stat, I think, in my opinion, for flight. And that's the fully charged time. So what the fully charged time telemetry field gives you is how long the battery has been charging, where the charge current has dropped down to be less than 50 milliamps. So what that means is, and the battery hasn't started to discharge more than 50 milliamps. The fully charged time means how long the battery has stayed in that status of being more or less fully charged. And it's really the only thing that tells you what your power margin is on orbit. We don't have any way of determining how much power the solar arrays could generate. We only know how much the solar arrays are actually generating at the exact moment in time. And we don't know how much more power the solar arrays could generate. So we don't know that the power that we're drawing from the solar arrays is either 10% of the solar array power, or if it's 99.9% of the solar array power. Fully charged time gives you an idea over the course of a couple orbits of how long that battery has stayed fully charged. If the time is a little bit, like 5 minutes per orbit, it means that the amount of power that this is available on the solar array is pretty close to the amount of power that you need to run the satellite and charge the battery. Versus if your fully charged time is long, like 15 or 20 minutes or 30 minutes of the sunlight phase of the orbit, that means your battery is charging super fast when it's in the sun, which means that either there's a ton of power available, or the battery didn't discharge very much during the eclipse, or both. And that means that your margin is quite high. It means you can, double the amount of charge into the battery if your fully charged time is after your sunlight phase your orbit. So it's a very useful stat for actually figuring out what is going on. And then lastly, we have a message log for debugging the actual EPS itself. That's basically it. That's the whole software. And there's some bugs, but what can you do? Anyway, thanks for watching.